Okay, we're starting a video here on applications of problem solving, products of vectors, and problem solving is very important. So let's have a look at this footy field here. We've got two guys playing. One guy, well, that's little Torquil there, and he's a pretty quick runner, and yeah, good fella, and he's up against Mongo. Now Torquil's pretty quick, and you know, agile guy, and he's running that way, and he can run at 20 kilometers per hour. That's pretty quick pace on the football field. Mongo, opposite direction, not quite as fast, 16 kilometers per hour, but you know, he's going. And you know, we're not that far removed from the ancient Romans, who loved a bit of gore in the Colosseum. Bang, there's some action, and yep, the crowd loves that, and collision occurs between the two bodies, and yep, Torquil's head's come off and he's in trouble. So not good news for him. So this is an example of the phenomenon of momentum, which the crowd really loves to watch. So the momentum P of an object is the product of its mass and velocity, and as such is a vector quantity. You can see the symbol there is P for momentum, or you can use boldface P as well for momentum. And you can see that we have the product of m mass and v velocity will give the body or the particle its momentum. Mass is a scalar and velocity is a vector quantity, and that's an example of a scalar multiplication of a vector giving another vector. We've seen that mathematics before. So we are interested in analysing the behaviour of systems of particles in collisions between objects. For example, like those two objects, those two players, one's head came off. Momentum is conserved. That means it's the same before a collision and remains the same after a collision. Now we've got a spinning top. It's got no linear motion, so it's got no straight line motion. It's spinning there on the spot. So we've got no v, vector v, so we can't use P equals m times v, the previous relationship. We need something else. We need to consider the rotational motion, so it's spinning round and round. It's called angular momentum, and its symbol is vector L. Vector L, it can also be written in boldface, and vector L is vector R crossed with m times vector v. You can see that there. The angular momentum L of an object of mass m, which is moving with a velocity of v, that means a point on its circumference has an instantaneous velocity of v, and it's spinning about point O, which should be the vertical member you can see there in the picture. The units are a bit strange. We've got kilograms meters squared per second, which can also be written in this form here, kilograms meters squared per second. S to the negative 1 means over S, doesn't it? You know your index laws. So that's the units. You can see where it comes from, because with linear momentum, linear motion, regular momentum, we've got kilograms meters per second because it's mass times velocity. With this one here, we've got an extra element in there. We've got an r, which is a position vector, which is basically a distance, which is basically implies another meter dimension to the unit. So instead of kilograms meters per second, we've got kilograms meters per second, or kilograms meters squared per second. Let's look at an example. So we have an object of mass 1.5 kilograms is moving with a velocity given by that vector v. Calculate the angular momentum of the object about a reference point O when its position is given by that vector r, as you can see. We start by writing down the given formula for it, and we predict that it's just going to be a straight application. So we clarify now by drawing out the correct parts given in the question, and correspondingly we put them with the parts in the equation, which you can see occurring on the screen right now. We do that carefully, and we make sure we've got r cross with m times v in the correct order, because as we know from our recent work, cross products are not commutative. We cannot change the order of the product and expect the same answer. So it has to be done in that order. Okay, and so the scalar multiplication is done first. So 1.5 outside of 2i minus 2j becomes 3i minus 3j. But then we do the cross product using the determinate method, which is one of the key methods we can use for a cross product. You can see that occurring there, and you can see the other parts of the working there. You may wish to put in an extra line of working after the 2 by 2 determinants. You probably will, because you're just getting used to using determinants. The result is a negative 9k, and we need to put in those units. So we write them in kilograms meter squared per second in either of the two forms you see in front of you there. Kilograms meter squared per second. So it's negative 9k kilograms meter squared per second. Being a vector, it needs to have ijk after it. Some just general problem solving tips with these sort of things. Remember to predict what's probably going to be involved in here based on your initial impression, your initial look at it. Clarify, which means what information has been given. What do I need to find? And in particular, especially consider if it is multiplication by a scalar or a dot product or a cross product. It could be one of those. Then do the maths, solve it, showing your working. Because once you've done step 2, step 3 is a logical progression from there. And reflect. Is my answer reasonable? Does it make sense? What sort of quantity am I expecting, and what sort of quantity have I got? Should it be a scalar? Have I got a scalar? Should it be a vector quantity? Have I got a vector quantity? Have I got the appropriate units on there? Does the size or the magnitude of my answer seem appropriate? So now you can do some problem solving with vectors and their multiples and their products.